This is a recorded webinar and video demonstration aiming to help originators of ship-based data get the most out of bottle salinity analyzed in the lab. It's made as part of the EuroGO-SHIP project. First, I'll talk about why you should measure bottle salinity, then about how it's done in general, and then slightly more specifically, talk about the range of different approaches that we found in EuroGO-SHIP were being used by different parts of the oceanographic community. I'll outline some key recommendations, aspects of sampling and analysis practices that seem to make the most difference for data quality, and then use a video to demonstrate some of the analysis steps using a common model of salinometer. So why measure bottle salinity? Well, first we need high-quality measurements of salinity to understand not only ocean physical processes, but also biogeochemical processes. We commonly derive salinity from conductivity and temperature, and the sensors we have available for these are very good, but they do drift, or sometimes even shift. So we collect water samples from the CTD Niskins or from the underway surface seawater supply, and measure their salinity in the lab, where we can use reference materials to make sure the data are accurate, then use those bottle salinities to calibrate the sensors, obtaining much better data quality, so that the data collected on each cruise are consistently comparable with data from other cruises, and we can have more confidence in the differences in space or time. Some projects have a focus on ocean hydrography and measuring physical processes, so calibrating salinity with bottle samples will be a default there. But many other projects, for instance fisheries cruises, also measure salinity as part of the background to the observations that they're primarily focused on. And one of the aims of EuroGO-SHIP was to outline how the quality of all sorts of ship-based data can be increased to improve the overall data set available. And calibrating salinity is one way, and that's something I'll come back to. First, I'll outline how we measure bottle salinity. Water samples to match to the sensor data are collected either from CTD Niskin bottles or from the surface seawater supply of the TSG. So the sample bottles need to be rinsed, then they're filled, leaving a small headspace, and then sealed to prevent evaporation. Then we use a salinometer to precisely and accurately measure the conductivity of each sample at a known temperature. Salinometers come in different models, but they work by drawing a small volume subsample from each salinity sample bottle into a cell inside the instrument, and there are a couple different methods for reducing evaporation while you're doing that. Then they heat or cool the subsample to a set known temperature, and this uses a water bath. The whole sample bottle might also be immersed in a water bath to make sure it starts out at near the right temperature. And the temperature of the water bath may be monitored, or it may just be set using a thermostat and lamps. Then they measure the subsample's conductivity relative to a reference conductivity, and generally manufacturer-supplied software can be used to record the conductivity ratio over a time interval of several seconds. You then adjust for any offsets in the salinometer itself by also measuring IAPSO-certified standard seawater as a reference material. And finally convert this conductivity to salinity using the known temperature and the equation of state for seawater. So this is the outline, but you may have a few questions about the details, maybe starting with, well, how many samples do I need to collect? What kind of salinometer do I need to use? Does it matter? And how often do I have to do this adjustment by measuring standard seawater process? As far as how many samples and standards, to some extent the answer is it depends. It depends on what you need from your data and what you are able to do. So there are a range of approaches for both samples and standardization, and broadly that can be organized from lower cost but lower accuracy to higher accuracy but higher cost. At one extreme, you might not take any samples at all, just rely on the factory calibration of the sensor. But then, especially if you only have one CTD, you're likely to have an unknown error. in the middle of this range, you might take a few samples and make a single adjustment to the data from a cruise, and you would run a couple of standards before you analyze the samples. But what you're missing in this case is information on the depth dependence of the calibration, which can be important, and possibly also on the drift over the course of the cruise. Depending on how long it is, this could be significant, and it could be something significant that you're aliasing into the data you're collecting from different locations. Or you might take more samples. You might take samples from many of the Niskins for salinity, but because of where you want to sample other things, either because you don't have enough water from every Niskin or because you only want to fire Niskins at certain depths, maybe you only collect water from near the upper ocean, or maybe only from the deep ocean. And you might also monitor the salinometer standardization a few times or daily as you're running the samples in case it needs to be changed. So this is going to improve the data quality, but if you're not getting the full depth range, you're still missing important information because of the pressure dependence of the conductivity calibration. And then on the high effort end, sort of summarizing the GO-SHIP procedure, you might collect a salinity sample from every Niskin you're using on every cast. You'd make sure the Niskins are distributed over the full depth range, and you would also collect salinity samples from the underway surface seawater to calibrate the thermosalinograph. And you will measure more than one certified standard per batch of samples and use all of the offsets measured to fit a trend to the salinometer standardization and correct the sample data for that trend. This can give very high quality, low uncertainty data, but it is expensive in terms of buying standard seawater. It takes quite a bit of someone's time to run that many samples, and especially as ocean biology becomes part of routine observations, there may not be enough water in every Niskin for all the parameters you want to measure. So given that there are these trade-offs, there's not a single answer. Instead, the question is, what are the most efficient things to do to get the highest quality data given our constraints on standard seawater purchases, staff time, equipment and lab space at sea, and other demands on Niskin water or sample distribution? So first, if you can, do take more samples, and if not, prioritize their distribution. So for calibration, you want to sample over a range of depths, and you do want to especially sample from points with a low background gradient in salinity, because those will give you the best comparison between the CTD and the bottle sample with the least noise. And then next, however many samples you can collect, get the most out of each of them by following good sample collection and analysis practices. So as far as sample collection, these are some things to keep in mind, some common mistakes that came up in some of the EuroGO-SHIP exercises that should be avoided. Contamination of the sample from splashes or rain, leaving too much headspace in the sample bottle that allows too much evaporation while the sample is stored. Leaving no headspace could allow the seal to be broken as the sample heats up. Rinsing the bottle caps in water from the Niskin. So there are some samples, like nutrient samples, where this might be typical practice, but for salinity, you don't want to do this because you will end up with a non-sealed part of the cap that it has salt water in it. You'll put it in the air-conditioned lab. That will evaporate. It will leave salt crystals, and when you open the bottle, they may be knocked into the sample and throw off the sample. And similarly, you don't want to contaminate the sample as you're closing it by having salt crystals on your hands or your gloves or the towel you're using. Another problem is not properly sealing sample bottles. It's just something to point out to your samplers to be careful with. And finally, storing samples for more than 4 months. They do degrade. As far as analysis, there are some things that depend on the salinometer model you're using, but of course it is important to maintain the salinometer. Another key is to maintain consistent ambient sample and salinometer temperature. So as much as possible, don't work in a space that has a lot of traffic, doors opening and closing, or otherwise doesn't have good temperature control. If it's possible to monitor the lab temperature as well as the salinometer bath temperature, that's useful. And consider using an external water bath to bring the samples to the temperature they need to be. It's both faster than air, and it gives you better control than relying on the air conditioning in your lab. When you're measuring the standardization of the salinometer, always use an in-date bottle of standard seawater that you've just taken the seal off of. So don't remeasure one that you've used a few samples ago, an hour ago, even if you put the cap back on, because it will have changed and that will throw off your samples. You can use open bottles or specially made substandards to monitor the salinometer performance, though. And finally, take advantage of replicates and averaging to reduce the uncertainty. So use more than one bottle of standard seawater when you're initially standardizing the salinometer. Monitor and record the changes in the standardization offset using, again, more new bottles of standard seawater throughout the time over which you're running samples, ideally at least 2 per analysis day. And record measurements from 3 to 4 replicate subsamples from each bottle, whether sample or standard. These independent measurements do help reduce the noise. We'll demonstrate how to use an autocell salinometer to measure salinity. In this configuration, it uses a peristaltic pump here, as well as the internal pump, to draw water from a sample bottle placed here into the conductivity measuring cell here. The conductivity cell is immersed in a bath, which is kept at a set temperature by 2 lamps. You can select the set temperature here. The room temperature should be close to the bath temperature, and the sample bottles must be stored for long enough in the room that they equilibrate to that temperature, so that when a small volume of sample is drawn into the conductivity cell, it can be warmed or cooled to the set temperature of the bath within a few seconds. Conductivity is measured in the cell when this knob here is turned to read mode. And by knowing conductivity and temperature, we can back up the salinity using the equations of state of seawater. The conductivity reading will be displayed on the screen here. For the autocell, that is twice the ratio of measured conductivity to a reference conductivity, but it's also advisable to record it digitally using software. This salinometer bath was filled yesterday, so now that it has had time to come to the set temperature, the water is circulating and the lamps are flickering off and on to keep it at that temperature, we can standardize the instrument. We are about to measure what the instrument reads for standard seawater of a precisely known conductivity ratio, and that value will affect every other data point. So even a tiny amount of distilled water left in the cell could throw off this measurement relatively a lot. So first we take an old or previously opened bottle of standard seawater and use that to flush through several times. Turn on the peristaltic pump, cover the flush valve to allow water to drain from the cell, uncover it to refill the cell from the bottle, and repeat several times. The conductivity of this old bottle doesn't need to be recorded since we know that it will probably have gotten saltier through being unsealed, but you can check the reading to make sure it's around what you expect. For this model, that will be 1.999 something. Once it's close, take a brand new sealed bottle of standard seawater and overturn it thoroughly to mix. You want the bottle to be well mixed without introducing too many bubbles. Although large bubbles will rise to the surface, the very small ones will rise slowly or stick to the side, and they may then be drawn into the sampling tube and then get stuck in the conductivity cell. When you are ready to run the standard, after mixing, carefully remove the foil seal and the rubber bung. When swapping out the previous bottle, use a tissue to avoid contaminating the new bottle or the tubing. You can catch any droplets from the old bottle that might be left on the tubing and keep any salt or dirt on your fingers from being introduced into the new bottle or onto the tubing. Now turn on the peristaltic pump to the middle speed. Cover the flush valve with a finger. This causes the water from the cell to drain, you can see here, and let that continue until there's only a trickle. Release the flush valve, and this will allow the cell to refill. Check that the whole cell is filling without leaving a bubble. Now the cell has refilled once. Again, cover the flush valve and empty it, release, and let it refill. Repeat this flush and fill procedure a third time. Then switch off the peristaltic pump. Wait a few seconds and check that the lamps in the bath are switching off and on to indicate that the sample in the cell is the right temperature. It's not needing to be uniformly heated or allowed to cool. Then you can switch the function knob to read and wait a few seconds for the displayed number to stabilize. This should stabilize in much fewer than 10 seconds. If you notice the number is fluctuating wildly or very far off the number you expect, the first thing to check is whether there is a bubble in the cell. If so, switch back to standby, flush and refill the cell, wait, and switch back to read again. If this keeps happening, you need to clean the conductivity cell. On the other hand, if the reading is changing more slowly, that may indicate the temperature of the water in the cell is still adjusting. In that case, you should again switch back to standby and wait for it to equilibrate better before switching back to read. If the reading is consistently drifting fresher over time, you may have a leak and should service the instrument. Once your reading is stable, adjust the standardized knob so that the displayed value agrees with what is shown on the standard seawater vial. Again, for this instrument, the displayed value is twice the conductivity ratio, so in this case, for this batch, we're looking for 1.99970. We can switch back to standby, and again, this is important to do here to avoid electronics overloads, which introduce error to the reading, and then draw another sample from the same bottle by flushing and filling once. Switch to read, and you can see how it initially starts higher, but then stabilizes about 1.99970. And we can repeat this a third time from the same bottle. Standby, flush and fill, pause, read. Repeat that. If this is the first standardization after the instrument has been set up in this lab, it is advisable to repeat what we just did with 1 or 2 more bottles of newly opened standard seawater. But now that the standardization is correct, we hopefully won't touch the standardized knob again. Instead, before running samples, we will check the standardization by measuring a new bottle of standard seawater. We'll record that measurement and subtract the offset from what it should be from all the samples. So let's say we have standardized the machine, and now it's a few days later, we have samples to run. So the cell has been filled with distilled water in the meantime, so we will again start with several flushes of an old bottle of standard seawater. Then we'll take a new sealed bottle, remove the seals, and the new bottle is inserted carefully using a tissue to dry any droplet on the tube. After 3 flushes and fills as before, we let the temperature stabilize, switch to read, and check that the value displayed is still nominal. Record the value, then we draw another sample from this bottle by switching to standby, flushing and filling once, switching back to read. And then we can measure and record a third sample from this bottle, again checking the cell is completely filled, the bath is stabilized before we switch to read, and the reading displayed is stable as well. To decrease uncertainty, you can repeat for a fourth sample from the same bottle as long as it's over 20% full. Now that we have recorded the conductivity readings for 3 or 4 volumes drawn from a newly opened bottle of standard seawater, we can start with our ocean samples. It's important to check the sample bottles as you go. For example, this one has not been filled enough and has probably had evaporation into the large airspace at the top of the bottle. This one has been filled correctly, leaving a small airspace, but when we remove the screw lid and examine the plastic insert, you can see it has not been properly pushed down to the bottle lip all the way around. This bottle here is full enough, so we log the label number, then gently agitate by overturning, again to mix the water without adding small air bubbles that could get stuck in the conductivity cell. We check that the insert has provided a good seal, then remove the plastic insert. A clean table knife is helpful here. Check the lip of the bottle once the insert is off to make sure there are no salt crystals, because knocking a single salt crystal into the water could significantly change the salinity. If there are any droplets or crystals on the outside, carefully pat them off. Now place the tube into the sample bottle, again using a piece of tissue to dry any droplets from the tube. Switch on the peristaltic pump, cover the flush valve to empty the cell, and allow the cell to fill completely with water from the sample bottle. Flush and fill again, and again. Turn the peristaltic pump off, allow the volume in the conductivity cell to equilibrate to the bath temperature, then switch to read. Here the display is flashing and has a minus sign in the middle because the sample we've just started measuring is much fresher than the standard seawater. We therefore turn the suppression knob down until the display stops flashing and shows a plus sign. Now we can let the value stabilize and record it. If you're using a computer program with an automated delay and you miss the fact that the suppression needs to be changed, this can produce erroneous readings. So even if you are using a computer, it's important to attend to the display as well as the bath window, and useful to also note values on a log sheet as backup. If you're not using a computer program, then keep in mind that you should take the reading over about 10 seconds. Switch back to standby, turn the peri pump on, flush the cell and allow it to fill. Turn the peri pump off, let the temperature adjust, switch to read, let the reading stabilize, and record the value for the second subsample from this bottle. Repeat this for a third time. If your 3 readings did not agree within 5 in the last digit, you can repeat this for a fourth sample from the same bottle. If one of the readings from a bottle is a clear outlier, it can be discarded before averaging. But if you try to take more than 4 subsamples from a single sample bottle, the water level will be low enough and it will have been open long enough that evaporation within the bottle will start to be a problem, biasing the salinity. If you're noticing that the first sample is often an outlier, it's best to increase the initial flush and fill repetitions from 3 to 4 or 5. Now we go on to the next sample. Take the next sample bottle, agitate it, check the seal of the insert, open, and place into the salinometer. Start the peri pump, flush, and then refill the cell. You can record the bottle label while the cell fills. Flush and fill a second time, and a third time. Switch off the peri pump, let the temperature stabilize, then switch to read. Let the display stabilize, and record the first reading. Switch back to standby, turn on the peri pump, flush and fill the cell with a new volume from the same bottle. turn off the peri pump, let the temperature stabilize, switch to read, let the display stabilize, and record as a second reading from this sample bottle. Switch back to standby and repeat this a third time to record the third value from this sample bottle. When you have finished a set of samples, it's recommended to run and record another new bottle of standard seawater. So here we'd follow the same procedure as we did at the beginning of the set of samples, where we flush a few times with an old bottle of standard seawater to get the salinity close to the standard value. Then we take a new sealed bottle, follow the procedure to agitate it, unseal it, and carefully add the tube without contamination, flush and refill the cell 3 to 5 times, stabilize, record a measurement, flush and refill the cell, stabilize and record a second measurement, again flush and refill the cell, stabilize and record a third measurement. You want as many measurements of the standard as is practical so that you can average and detect drifts over time as confidently as possible. So again, every sample value is affected by the offset you'll apply based on the measurements from these standard seawater bottles. If you have concerns about how the machine is performing or about temperature control, or you notice that there is a large drift from the start to the end of the analysis, you may want to also run a bottle in the middle of the set, for instance, one at the start, one after 12 samples, and one after 24 samples. But this may not be within the budget, so you can also mix up your own substandard, ideally using deep ocean water in a large bottle and then decanting it into sealed sample bottles. And you can use that as a sanity check on whether the machine is drifting over the course of a run by running in addition to a standard, running a substandard at the start and then running just a substandard in the middle and a substandard at the end. You shouldn't use the offsets from a substandard to adjust the sample readings. They're just there to let you know if there are problems. When you're finished and are going to leave the machine for a while, then refill the cell with distilled water. Here we want to flush through most of a sample bottle volume of deionized water. We can turn the pumps up all the way in this case and keep flushing and filling repeatedly. Now let's check. Turn the peri pump off, switch to read. We'll need to turn the suppression down because it's already much fresher than the standard seawater. We're getting close to 0, but we'll do some more flushes and fills. We switch to standby, record the final standby value, then to 0, record that value. Neither has drifted significantly from the start. Finally, we switch off the internal pump as well, but leave the salinometer on to keep the bath temperature ready for the next set of samples you need to run.